This video is about finding kth largest element in an array, and that array is not guaranteed to be sorted, so it is an unsorted array. Let's say we have some elements in an array. So we have 3, 2, 1, we have 5, we have 6, and then we have 4. K is equals to 2 would mean second largest, and we know that 6 is largest and 5 is second largest, so 5 would be the answer. A straightforward approach in order to solve this question would just simply be sort the array. So we sort the array and we get 1, 2, 3, 4, 5, 6. This is how the sorted version looks like. We have on 0, 1, 2, 3, and our index at 4 and 5. And by k, it would just mean that you just pick this k from the end. So if k was 2, I can just pick -2 from the end, and I would get my value 5. If you talk about space complexity and you talk about time complexity, so it's n log of n, because sorting is actually what takes place. So this is n log of n, and then if you have to just access an element from a given array, it's just a constant time operation. So it's mainly the sorting operation which is taking a lot of time. If you think about a solution which is not sorting oriented, and that's because, let's say if I have n as 1 million items and my k was 2, what I'm trying to do through sorting is that I'm actually trying to sort 1 million items or 1 million elements just to find out a single kth largest value. So instead of sorting, what if I would try to actually find k elements? Although this question is about finding kth largest, and definitely I'm sticking to that, but what if I just try to find out k elements and then I pick minimum of those k elements? So let's see if this is a legit approach or not. And for that, let's say I have the same array, which is 3, 2, 1, 5, 6, 4, and 4, and my k is 3. So if I just pick, I know that I have to find the third largest, and here's a simple trick if you don't want to use sorting, because we have clearly seen that sorting 1 million items just to find that single kth largest value is where a lot of time is being computed. So if you have these elements with you, and if you try to find top k elements, what would that mean? That would mean we have 6, we have 5, and we have 4, and then from these 3 elements you just pick the minimum one, which is 4, and that is going to be your kth largest element. So if I have this understanding and if I have this intuition with me, that instead of sorting n elements, this is not the approach. I take another approach, is just find top k and then find minimum of that top k. So that can definitely bring down my time complexity, and I can show you how. And before moving towards time complexity that's reduced, let's just see which particular data structure can be useful in this particular situation. This kind of hints me to use a minimum heap data structure, which can just actually hold k elements, and then because it's minimum heap, I would definitely be having my minimum element at the root of that min-heap. If we move towards dry run, that is where things will actually become more clear. So the dry run looks like we have 3, 2, 1, we have 5, 6, and 4. For the sake of example, I'm taking k is equals to 2. So let's try to process it element by element and see what is actually happening towards heap. So I have 3 right now. I'm scanning this array, so I'm at 3 and my heap is empty. So what am I going to do is I'm just going to insert it. So it's just a push operation or insertion operation for my heap, and then I move towards 2 and I see that the heap is not empty, but the size of the heap is currently 1. Let me just also keep a variable for size of my heap right now, which was initially 1, which is not equal to k. So I'm just going to push 2 in the heap, and since it's a minimum heap, so 2 will be at the root at the top and 3 is pushed down, and then I move towards 1 and my size was 2 when I did this part. So when I move towards 1, that's my element right now, I cannot just push 1 blindly because my current size is already 2. My size is already 2. So I would see that is my incoming element from the array, which is 1. Is it greater than 2 or not? Because the entire purpose of this heap is to actually hold top k elements, the logic that we just discussed here. That can I have some kind of data structure and this logic that I am just holding top k elements instead of holding instead of holding all the elements, which was in the case of sorting. So I just make this comparison. Is 1 greater than 2? No. So that would mean that till this point, it's actually 2 and 3, which do exist in my top 2 elements. So I would not push anything and I would also not pop anything. So my heap is just still looking like this with 2 at the top and 3 as its child node. And then I move towards 5. So 5 is my element and I'm going to see the same thing. Is my 5 greater than 2? Yes, it is. And I can't just push it right away because I already checked that my size is already full. So when the size is full, you actually make a comparison between the incoming element of the array and the element which is minimum of the heap. And you see, is 5 greater than 2? Yes. If it is greater than 2, it's going to hint that these are not the top 2 elements up till now. And we can clearly see at this point, I should be having 3 and 5 as my top 2 elements. So I'm going to pop 2 and then I'm going to push my 5, which would mean that I have 3 and I have 5 now in my heap. And that is how it should actually look. Then I move towards 6 and my size is full again. I would make a comparison call. Is 6 greater than 3? Yes, it is, which is true. So I'm going to pop 3, whatever element was at the root, which was of course minimum at that particular point. So I pop 3, then I push 6, and now my heap looks like this, 5 and 6. And then I'm going to move towards 4, the last element in the array, and I'm making the same call. Is my size full? Yes, it is. Is 4 greater than 5? No. If it's not that case, if both of them are false, just don't do anything. So my heap still looks like 5 at the top and 6 as its child node. And now my entire array has been traversed and I would just stop here. And what am I going to do at this point is I'm going to take a look how my heap looks like. So I'm just going to redraw it here so it's easier for you to recall. So I have 5 and 6, and if you see which ones are the top k elements, so of course they are 5 and they are the 6. And then I'm just going to pick minimum of 5 and 6. So I'm just going to pop and I get my answer 5. Now let's see what's actually the time and space complexity of this particular heap data structure and the algorithm we just walked through. So we can just quickly see that I did 2 important operations. First one was traversals. So I was definitely traversing every element of the array, and that's going to take n, big O of n. And if you talk about the pop and the push operations, for heap they are log n. I'm not going into the details of why it's log n because again I'm assuming that you're someone who has a know-how of searching and sorting algorithms and common data structures. So in the worst case, I mean, for every n element, I will need to, it's not going to be log n, it's going to be log k. In the worst case, it's going to be n log of k. Why? Because for every n elements, let's suppose if the array that was given to you was actually already sorted. So in that particular case, you will have a push operation and you will have a pop operation for every element, and it's k because at most or at maximum the height or the size of the heap is going to be k. That's why it's actually log k. And if you compare this with sorting, we earlier had time complexity of n log n instead of n log k that we now have through heap. Of course, because it's big O of k in heap, which is the space complexity, whereas for sorting it was big O of 1 constant because it was in place. So definitely we did trade off space complexity here, but we were able to bring it down towards n log k. So that's it, that how we can use heap in order to tackle this problem. When you actually see trends or patterns in questions where you have to find top k or you have to find largest, and of course it's not about memorizing these keywords, it's actually about recognizing the patterns. The pattern which was actually simply here where you have top k problems and you can translate that problem description or that problem understanding into size k heap. That's one of the patterns that can actually show up in a lot of interview questions, and they can be kind of solved through the similar approach. So that's it. The pattern is what matters, and instead not memorizing the syntax. If you know this pattern, then the code just comes itself. And that's why I'm not going to include code in any of my videos. It's more of the thinking model that I'm trying to focus here. And see you in the next video.